In this lesson, we're going to consider the internal resistance of a power supply, like a battery, a generator, whatever. And this is really important in a practical sense. It is the existence of this internal resistance is the reason why a small little 12-volt battery, for instance, well, not a car battery, but say 8 of your 1.5-volt AA batteries connected in series. That'd give you 12 volts. Why couldn't you hook that across a car and start the car up? Why do you need this great big lead acid battery that sits in your car that weighs, 50 pounds or whatever? It's because of the thing called internal resistance. It's the reason why a battery cannot supply an infinite amount of current, which I'm sure you would guess anyway to be the truth, that a battery isn't going to be an unlimited source of current. But what limits it? I'm glad you asked. It's the internal resistance. And it's because of that that you need to work really hard to reduce it down to a point where you can draw several hundred amps out of like the batteries in my truck. It's a dual battery system. Needs to pull several hundred amps at, somewhere between 8 and 12 volts to start the truck. And that requires a whole lot of current. And it requires an internal resistance that's very small. So we're going to define EMF first, and EMF is electromotive force, which I say is a bad name because it's not really a force. As I'll explain, the symbol is this epsilon here. It is actually the potential rise inside a battery from chemical reactions. So inside a battery you have a chemical reaction going on, it separates charges, and that separation of charges results in a voltage rise, or a voltage change, a voltage across the battery. So really EMF is voltage, and it's not force per se. The idea originally was, hey, this is what causes the charges to move. But charges are moved by electric fields pushing on them, not by a voltage. Voltage is energy per charge. But in a practical sense, it's often fine to think of a high voltage pushing harder on a charge because it is so associated with a higher electric field, which does push on the charge. Okay, enough of that background. Now, the EMF, which is a property of the battery itself, the chemical reaction that separates the charges, it's different from the battery terminal voltage. The battery terminal voltage is what you would read by putting a meter across the battery. It's different than that in general. Now I'm going to explain that a little better. Okay, because the reason why, though, is because if current flows in the circuit, some of the EMF that the battery is producing is dropped across the internal resistance. R internal, I typically call it small r. So now it's time to get a model of a battery here. So here's, I'm showing like a car battery. And there's the terminals A and B. And look at the internal resistance here, the internal resistor. Just putting that there. It doesn't really exist there, but this is a model. And it's a model basically is an approach which gives us correct answers, the way to view or the way to consider how a system functions in simplistic terms that is consistent with reality. So in the dashed lines there, I'm going to draw a battery. You've already seen the battery symbol, negative and positive, short and long lines respectively. And there is battery terminal A, the battery terminals right there. All right. Now, the EMF is developed across the battery, the basic battery function itself, the chemical reaction. So let's say that's 12 volts. And we have battery terminal B. And a current that, in general, will be flowing. Not yet, because we don't have a circuit. But what I'm going to stick in the middle here is the rest of it, which is this internal resistance. There it is. Effectively, it's like there's a resistance inside this battery for the current to flow. How's that for a subscript? R sub internal to battery or power supply. So there's our model. And now what we recognize is as current flows, you notice you have a plus to minus drop across this battery. That means there's a voltage rise in this direction. Here's a rise this way, the battery function itself, the EMF of the battery, but because of the internal resistance of the battery, when current flows, it produces a voltage inside it which opposes itself. This is itself, the EMF. And this opposes itself. All right. And so if you're kind of following this, you're going to look at this and say, wait a minute. What's available then from A to B is less than the EMF by this amount. If you're thinking that way, you're thinking well. Thank you very much. And I'll go through it again before the slide is over. So here we have the terminal voltage, VBA. That's really all you have direct access to. You take a meter and put it across the terminals. You can't go inside and figure out what this is doing. You have to interpret it by what you see on the terminals. So here's now our circuit. We have an external resistor. All right. And so the question is this. VBA, the voltage of B from the point of view of A. So you put the negative lead on A, the positive lead on B, and you read a voltage, whatever it is. Now, that's the rise in voltage from A to B. Now, is that going to be the same, less, or more than the EMF of the battery? Answer is, we've already answered the question. Because of the direction of the voltage change across this resistor, because it's going from positive to negative, it's dropping across here, it's less than the EMF. All right, now I've already answered the question, but I'm going to answer it again. As current flows in the external circuit, and what's in the external circuit is this I. It's everywhere in the external circuit, and actually internally as well, right? Because really this whole thing is a series circuit through the entire system. There is a voltage drop. What's that voltage drop equal to? IR internal. This is it. This is the voltage drop. And that causes the terminal voltage, what you measure from A to B, to, that's VBA, right? Voltage of B with respect to A, to be less than the battery EMF by the amount, this amount here, IR internal. So we can write that as an equation, namely the terminal voltage that you see is equal to the EMF produced by the battery minus IR internal. And that's your equation that relates the EMF, the terminal voltage, the current flowing, and the internal resistance. There's a little interesting thing here that I just want to mention before I stop this little lesson, and that is you can figure out what the EMF is. How? By making the current. You can't change this R internal. That's a characteristic property. But you can change the current, namely take away the external circuit. No external circuit, no current. Then the terminal voltage of the battery is equal to the EMF. So grab your battery, don't hook it up to anything, but put a voltmeter, which is really, really high resistance. It's just sampling the voltage. When you go VBA, then you're going to be, there's no drop across here, so you really are reading the EMF. So the battery EMF can be determined by measuring the open circuit voltage across that battery. Just read the voltage right across the battery. But as soon as you put an external circuit in and current flows, if you keep your voltmeter across there, you'll see the terminal voltage drop. More to be said about that, but that's a good introduction to what we mean by internal resistance, and we'll call that a wrap for now.